A single box plot like this one is a slightly less detailed than a histogram graph for one quantitative variable. So in this case, we're looking at Lake Travis water levels from 1980 to 2016. And this is really a visual representation of the 5-number summary. So in the middle of the box here, we have the median. The bottom of the box is our first quartile Q1, and the top of the box is our third quartile Q3, which means that the box itself represents the middle half of the distribution. Remember that Q1 is the 25th percentile, and Q3 is the 75th percentile. So everything that's between the 25th and 75th percentile is the middle half. Up here at the top, we have our maximum. And we call these two bars that come out from the box whiskers, just like a cat has whiskers. Some graphs put a little stopping point that's a little more clear. Some graphs have those whiskers just kind of stop. Down here at the bottom, any sort of marker that's off the end of the whisker, it could be a star like these ones are, it could be an open circle. These are the outliers. So the lowest outlier in this case is also the minimum, and this lower end here is really my minimum without outliers. So it's the smallest value in the data set that is not considered an outlier. And the same for the maximum. That's the maximum without outliers. So the actual true minimum and maximum would be the highest and lowest outliers if there are any. So looking at this, we can describe the shape and center of this distribution. I'm going to clear all of this before we go on to answer these questions, just so that we can mark it up again. To describe the shape and center, first of all, I can see the center that's easy to see here is the median. And I'll estimate its value at about 673. As for the shape, I can see that it has some skew because of the fact that one whisker is longer than the other. So we have a short whisker up here and a long whisker down here, and we also have our outliers in this direction, which means that this is the direction of the skew. We have a longer tail on this side. What we need to decide now is that left skew or right skew? And so looking over here at the numbers is our clue about whether that tail would go in the direction of smaller numbers or bigger numbers. We can see that that goes towards the smaller numbers. And if this were a histogram oriented more left to right, then that would be going toward the left. So the center is around 673, and the distribution has left skew. We've already seen a histogram for this distribution, and we have seen that it has left skew. But we can see it from the box plot as well. Estimating the middle half, that's where we want to see if we can identify the values that make the box, right? The upper and lower bounds of the box. And it looks like my upper half is very close to 680. I might call it 681. and my lower half is closer to 660. It looks like maybe 663. So the middle half is between 663 and 681. We've already identified the 4 outliers, right, down at the bottom. There are 4. They are all low outliers, so there are no high outliers. And looking at this distribution, remember that a symmetric distribution would have the mean and the median equal to each other. As soon as you have skew or outliers present in one direction, the mean gets pulled towards those outliers or pulled towards the direction of the skew. So the mean is going to get pulled towards smaller numbers. The mean would be smaller than the median in this case because of that skew and the low outliers. So we know that the mean would be a little bit less than that 673. Maybe we could estimate this mean to be about 670, right? Or maybe it would be a little bit less than that. Maybe it would go all the way down to 665. Usually it's not dramatically different from the median, but it does get pulled in the direction of the skew. It can be dramatically different if you have a really, really extreme outlier. We have so far defined outliers as unusually high or unusually small values in a data set, but we haven't really had a strict criterion for determining what is and what is not an outlier. The most commonly used is what we call the 1.5 times IQR rule, where we take both of our quartiles, the first quartile and the third quartile, and we go out an additional 1.5 times IQR from there. So if we recall for our Lake Travis data set, we found that IQR in the previous section. The Lake Travis IQR was 16.6. So that's the value we're going to use here. And we also found that our Q1 was 663.9 and our Q3 was 680.5. So to do this, I would first find 1.5 times the IQR because I'm going to use it twice. It makes sense to go ahead and just find it once. Calculator is helpful for this. We've already got 16.6 in here. I'll just multiply that by 1.5 to get 24.9. So that's the number I'm going to subtract from Q1. This is 663.9 minus 24.9, which turns out to be 639 exactly. And our upper bound is 680.5 plus 24.9, which turns out to be 705.4. So these are the bounds for all data values that we consider not to be outliers. So values between these two numbers are not outliers. And we would need to look at a list of this data in order to find the ones that are outside these bounds. The easiest way to do this is to come back to our section 2.2 notes where we had a sorted list, and we used this sorted list to find the median. So 639 is my lower bound, and that occurs right here. 705 is my upper bound, which is higher than the highest value on here. And I knew already that there were no high outliers from the box plot. So these are the 4 values that I want to write down as my low outliers: 624, 626, 628, and 632. So finally, my actual outliers are these values.